All right, let's go ahead and get started. So, most of you have probably already seen, but tests are graded, graded during Canvas. If you want yours back, you're going to have to wait a little bit. I got two more people who need to take it. So, as soon as that happens, I can get them back and I'll post solutions, things like that. Just like with the last one, if you have concerns, you want to talk about it one-on-one, let me know. And we can definitely make a time to do that. Or if you're concerned about kind of where you stand, I think we have like a week before the drop, the last data drop. I think it's November 1st. So yeah, I think that's exactly a week from today. So yeah, after two of the three midterms, should have a clearer picture than before, kind of where you stand. A couple things that I don't think I've said in class. I might have put an announcement, but at the end of the semester, if your final exam grade is better than one of your midterm grades, it will replace it. So there's a chance to get some relief there. I'll also be dropping one or more homework assignments at the end of the semester. So that'll be a relief. I mean, that'll definitely can't hurt you. So those things are coming. All that to say that, you know, those of you who are worried, a couple of you have reached out to me, and I'm sure there are others who are at least thinking about it. Things maybe aren't as bad as they seem from just the numbers. But if you have concerns, let's talk soon before that drop deadline. Good. Cool. Get back into series. So we're going to talk about some convergence tests. So basically, from here on out for the rest of the chapter, you know, sequences were more or less a means to an end. But series are going to be the thing that we're primarily interested in. So going from there, it's going to be a benefit to have a lot more tools to figure out whether series exists or series exist, whether they converge. So I think at this point, we've only really talked about, there are only really two ways you can tell me if series converge, right? We've talked about geometric series and telescoping series. But those are useful in only really limited cases. So let's get a little more general. So do these series converge? I know we've talked about one of these. Does that first series converge or diverge? So we talked about that one. That one diverges, right? Do we have any suspicion about the bottom one? What's the major difference between these two? What is each sequence doing? So as n goes to infinity, what does this sequence do? That goes to 0, right? What does this sequence do? Also goes to 0. So what does the numerator do? Alternates between -1 and 1, right? And what's the denominator do? It grows without bound, right? So you have a numerator that is bounded divided by a denominator that's not. So that's going to go to 0. But what do we think about the series? We know the sequence converges. But what does the series do? We have not talked about this specifically, and I'm very much looking for a guess right now. So thumbs up if you think it converges, thumbs down if you think it diverges. Okay, so the room is somewhat split. So let's talk about what can we do to know for sure. So there is a test specifically for alternating series, how to analyze whether they converge. So here's a very generic series. So what do all these different components look like? So basically, this series is basically the product of two things. One of those two things is essentially, this is basically the alternating part.
which means B sub n is non-alternating. It's either going to be always negative, always positive. But basically, we're going to decompose our, actually, no, we're going to treat it as always positive. Basically, we're going to decompose our series into two parts, an alternating part and a non-alternating part. That non-alternating part has to be positive. But not just that, it has to be, something else has to be true. What does this notation say right here? So for all n, b to the n plus 1, or sorry, b of sub n plus 1 is less than or equal to b sub n. What does that mean my sequence is doing as n gets bigger? It's decreasing, right? So all this to say that b sub n is, and I'll throw another word from last couple weeks in here, is monotone and decreasing. So if you meet all these conditions, so you have to have an alternating component. You have to have a non-alternating component that is positive and decreasing. If you have that, then what do you have? Oh, sorry, one more condition. We have to have that the sequence goes to 0. Do I need to say that? If you meet all those conditions, then you have a series that converges. So a lot of conditions you have to meet. So let's try to whittle this down into why this thing is really useful. Basically, we get to conclude that the series converges, right? But to make that conclusion, what are we really looking at? What's the thing that we actually analyze? We actually want to know what it's doing. B of n, which is what? Is it a sequence? Is it a series? B sub n is a sequence. So basically, if I have this alternating part, and I have this decreasing positive sequence B sub n, as long as B sub n goes to 0, then you have a series that converges. So a lot of definitions, a lot of conditions I'm throwing at you. How do we feel about that? We have questions about it. Can I ask us to vote on, hopefully I put it forward. Yeah, this one again. Does that change any of your opinions on this series here? Does this have an alternating part? Okay, so what is that? We'll call that A and B again. What's the alternating part? -1 to n. That alternates. If that's A, so then what is the other factor in this? What is the other part of this sequence? 1 over n. So we have our alternating part, we have our non-alternating part. Is this thing going to always be positive? Is it going to be decreasing?
Yeah.
Can I evaluate this? What is the limit as n goes to infinity of 1 over n? 0. And to be clear, I'm not looking at the series of 1 over n, I'm looking at just the sequence. Not what does the sum of terms go to, but what do the terms go to? So, since all those things are true, what can I say about the series? It must converge. So now we can say that for certain. So we know that when we add, if we add all the terms of the sequence 1 over n, it fails to converge. But if we let them alternate, then we get convergence. Questions? All right. How about this one? Can I use the new test we just talked about? What are the conditions of that test? Is there an alternating component? Yes? Okay. Let's identify it. What is it? -1 to n. Okay, what else? The other side. Always be positive. So let's identify the other part. What is the other like factor of this sequence? 3n over 4n minus 1. All right. Do we believe that? So we broke this thing down. It has an alternating part. Check. Now we have to answer some questions about the non-alternating part. Is Bn positive for all n? What do you think about that?
Yes.
Yes. Okay. Is it decreasing?
Yeah.
We got 1 vote for yes. So we can look at a few terms here. Bn is equal to, what's the first term? 1. And then 6 over 6/7. Then 9/11.
Yeah.
Okay. So maybe not obvious yet, but I believe, yes, it's going to be a decreasing sequence. Okay, so that's good. What else should we look at? What is the limit? I need it to be 0. So what is it? It's 3/4. So I didn't meet all the conditions for my theorem, which means I can't really use it. But did we learn anything else that's valuable? Do we have enough? Do we have other information that we can say whether the series converges or diverges? What converges to 3/4?
The sequence.
The sequence converts. So, and I need to. We got more than one sequence going on here. Which sequence converges to 3/4? B sub n. So we know that B sub n. So we learned this piece of data. B sub n converges to 3/4. Does that tell us anything about the series? Go ahead.
Like the convergence, like doesn't the series diverge?
Not because it converges, but because it gives you a little more specific. Because it converges to something that's not 0.
Yeah.
It is. It's not only that it's greater, but it's just that it's not 0. So since B sub n converges to 3/4, that means the series of A sub n, B sub n, that means it diverges. But that's not from the alternating series test. That came from something else, right? So that divergence theorem is pretty powerful and usually pretty quick to apply. So does the A sub n part of this converge, the alternating part? That can't converge, right? That's just going to bounce back between -1 and 1. Which means, like, if you were going to look at this series, the series of A sub n, B sub n equals, a bunch of stuff early. And then really what you're doing at the very end is +3/4, -3/4. So basically you're just bouncing back and forth, which means you're never going to settle on a value. So the fact that your sequence doesn't converge to 0 means your series is already going to be divergent. How we do? Right? How about this one? What should we look for? Do we have an alternating component? Yep. So alternates. Check. What else? Okay, yeah, let's call out those parts. What's A sub n? -1 to the n plus 1, and B sub n is equal to All right. What do we need to know about B sub n? Positive. How do we feel about that? Do we think it's positive? Should be, right? Is it decreasing? I don't know. Let's look at the two terms. What's the first term? 1/2. And then 4/9. And then 9/28. I think it's looks like it's going to be decreasing. At least it does for the first three terms. I will tell you that yes, it does. What else? What's the limit? So I need the limit as not b as b sub n does anything. As n goes to infinity of b sub n, I need that to be 0. Is that actually true? What's the limit as n goes to infinity of n squared over n cubed plus 1? Do you have suspicions? I see people doing the 0 gang sign. Question? Essentially, yeah, I mean, we can say this. It's just, I don't know, it's a little bit fraudulent. But yes, as n gets very big, the 1 in the denominator is going to get overwhelmed. So this is true. Something I'm going to encourage you to think about is this. The highest power on n in this whole sequence is 3, right? So what I'm going to do is this. I am going to divide both numerator and denominator. Or equivalently, basically I'm going to divide both numerator and denominator by n cubed. If I do that, then the limit I get is what? Or the expression I get is 1 over n over 1 plus 1 over n cubed. So in this way, I'm not really ignoring that 1, but I think this is another way to show that the 1 is going to get overwhelmed. So can I evaluate this limit? Numerator should go to 0. Denominator should go to 1. So I think I meet all my conditions. Okay, so what? I checked all my boxes. What do I get from all those?
The series convergence.
The series, and I'll just call it A sub n, B sub n. Series itself converges. And that all comes from looking at basically, it's not even like looking at the sequence, just looking at a part of the sequence, looking at one component of it. So we've seen a few examples now. Any questions on how to apply this test? How to make sure you actually can use it? We okay? Okay. So we know these are true, right? So we talked about last week this upper series diverges, and we just talked about a few minutes ago this lower series converges, right? So, and basically the only language we have so far is this binary thing of converge and diverge. So now I want to talk about this idea of absolute convergence and what that means. So basically what we have is this. The difference between these two series here is just that one of them has negative terms in it, right? But what if I did this? What if I took the absolute value of all the terms in here? If I take the absolute value of all these terms, would that make these two series identical? So basically I'm removing the alternating behavior if I take the absolute value. So that's what absolute convergence is kind of based on. If I have a series, then we can talk about it converging absolutely. or converging conditionally. So a series converges absolutely if I can take the absolute value of all those terms, add them up, and the series converges. So when you take the absolute value of something, what has to be the result? Like the absolute value of any number is what? It's at least what? We can't say positive for sure, but we can say it's at least 0. So there are going to be no negative terms in the sum that we're using to build up the series. If I can do that with my series and it converges, then I have absolute convergence. If I have a series where basically the base series converges, but me taking the absolute value of all the terms diverges, that's called conditional convergence. So now that I've thrown this new language at you, can you tell me about a series that converges conditionally? So basically a series that converges, but if I were to make all the terms positive, would fail to converge. We've seen it recently. Yeah, so this thing right here. Yeah. So this series right here. So let's ask a couple questions here just to drive all the definitions home. Does this series right here converge?
Yes.
It does, right? So we said this converges by the alternating series test. So it converges by alternating series test. So now let's look at a different thing. What happens instead if I do the absolute value operator on this sequence? How does that really alter this sequence? The n in the denominator is always going to be positive anyway, right? So the absolute value doesn't have any effect on that. But the numerator is the thing that alternates, right? If I take -1 to the power of n and take the absolute value of it, so I took a thing that either has values of -1 or 1. If I take the absolute value of those, what do I do to those values? So it's always what's the absolute value of 1? What's the absolute value of -1? So that becomes my only possibility when I take the absolute value. What do we know this sequence or this series does? That diverges. So what can we say about the convergence of this series? This is conditional convergence. Under some circumstances, it converges. So basically, under the given circumstances, it converges. Under, metaphorically speaking, the worst case scenario, where I take the absolute value of all my terms, it fails to converge. Questions about the definition of this example? We happy? Okay. How about this one? Classify the convergence of this thing. What do you want to look at first? Go ahead. Okay, so we're going to look at the alternating series test first. So what is a sub n? What's b sub n? -1 to the n, which means b sub n is 1 over n squared. Okay, so we have an alternating part. We have a few questions to ask about the b sub n. What are they? Is it positive? Okay. Are we okay with my symbols, or do I need to unpack a little more? So it's positive, right? I can do, you know what, I'll do both. It's positive. It's decreasing. There's one more thing we got to know. We got to know the limit of the sequence itself. So as n goes to infinity, what does 1 over n squared do? Goes to 0. Excellent. What have we learned? The series converges. So what kind of convergence do we have? Converges. Throw the adverb in this blank. Or, okay, we have conditional convergence. We good? We have at least conditional convergence, right? I think we have to do a little bit more digging. It might converge absolutely. But I think we have shown that it converges in some way. So basically, I've replaced our binary thing with a ternary thing. I have three possible results. Conditional convergence, absolute convergence, or divergence. We've ruled out divergence, right? Okay, so now we got to rule out some kind of convergence. So what can I look at? If I want to know something about absolute convergence, what do we have to investigate? The series 1 over n squared. So that is slightly different from what we have. How did we arrive at this new thing? The absolute value. So basically, if I take the absolute value of negative 1 to the n over n squared, same kind of logic as when we did negative 1 to the n over n. N's always positive, so squaring it is always positive. Are you okay with this right here? Basically, I'm just gonna remove the absolute value from the n squared. Do you agree that under our circumstances, those are equal? There's no way that n squared is gonna be negative anyway, so that absolute value is really doing no work. What does the numerator of that fraction become? Positive 1, right? So yes, that is where the 1 over n squared comes from. Do we know anything about the 1 over n squared series? I think we've talked about it really briefly. This converges. So let's talk about why. Now, we haven't really built it up. We kind of did with integrals, but here's there's a test that there's a section here that we're skipping that has some pretty valuable convergence tests in it, but I'll give one to you that's really quick. Let's say I have a series that is 1 over n to the power of p. This thing converges if p is what? Greater than 1. Did I say this, or are you bringing that in from elsewhere? Okay, cool. So that converges if p is greater than 1. We know that when p equals 1, that fails to converge, right? That's kind of the quintessential one that even though the sequence converges, the series does not. And it diverges on the complement of that. So if p is less than or equal to 1. So typically your test for absolute convergence will give you this thing. Well, it will give you a series that looks like that. But yeah, feel free to use that quick p series test is what it's commonly called. You can tell the convergence of that series just by looking at the power, as long as it's 1 over n to the some power.
What convert to 0?
No, we don't know what it converges to. So here's that's a very, it's kind of unsatisfying to think about this, but even though I know that this converges, I don't know if we know what it converges to. I think I kind of briefly alluded to this in class, but there are lots of series that we can say for sure converge that we don't know what their sums are. It's hard to think about. But we do know it converges. So can I fill in this blank? Converges absolutely. So let me ask you this question. If we would have taken the absolute value of the series first, would we have had to do the absolute with the alternating series test? So I know it's kind of hard to ask you to forget what we've done, but let's try. let's say the very first thing we looked at was this, the absolute value. And we saw convergence. Would that have meant we were done?
Yeah.
I got a vote for yes, and I saw some head shakes. So let's talk about these things. So we have divergence, we have convergence, absolute, and we have convergence conditional. Are there series which conditionally converge but don't absolutely converge? We've seen one, right? Are there series that converge absolutely but don't converge conditionally? So let's go back to the definition briefly. So if I take the absolute value of all the terms and add them all together infinitely, and they converge, that's absolute convergence, right? Is there a series where I can add up all the absolute values and get convergence, but then have some of them maybe be negative and then not have convergence? That's impossible. So absolute convergence, the word absolute, let that suggest something to you. If it converges absolutely, it converges under all circumstances. So a couple of different ways to think about this. Yes, if we would have tested absolute convergence first, we would have been done. But here's the flip side to that. If you test for absolute convergence and you fail, are you done? Because you don't know if you have conditional convergence or it just never converges. So those kinds of decisions will be more clear, I think, when we do more examples, when you do more on your own. But those are the kind of things you have to kind of come up with strategies to investigate. Not that I don't think that any one way we could have gone after this would have been significantly better or worse. How about this one? Any thoughts? Anything you can think of to look at? You can take the absolute value. So if we take the absolute value, so now we're gonna look at absolute convergence first of this thing. The absolute value of the cosine of n over n squared. What does that do?
Converges to 0,
How do we know that converges to 0?
because cosine is always gonna be 1. Or like between 1 and 0.
It's going to be between, so at the absolute value is going to be between 0 and 1, right? So I don't know if there's a cleaner way to say that than this. Let's keep the absolute value bar there, or the absolute value bars there. But a valuable thing to know here is this. You have a sequence that basically, based on what Tier has said, I think I can say this: -1 over n squared is less than or equal to cosine of n over n squared, which is less than or equal to 1 over n squared. Are we okay with that? Because cosine is never less than -1 and it's never bigger than 1. Tier also said this, that if we just think of the absolute value, then we have 0 is less than or equal to the absolute value of the cosine of n over n squared, which is less than or equal to 1 over n squared. So I'm writing these strings of inequalities. This look like a theorem we've looked at before. It's a squeeze theorem, right? So squeeze theorem only really helps us if kind of the least and the greatest sequences both go to the same thing, right? Do they? They do. They both go to what? Which means, here's what I found. I know the limit as n goes to infinity of cosine n. Actually, we did better than that, didn't we? Absolute value of cosine n over n squared. That limit's 0, right? Does that help? Are we done? I don't think it means we have absolute convergence. And why do I think it doesn't? What am I looking at here? That's the sequence. So I don't, the sequence itself doesn't tell me enough because I have sequences that converge to 0, but the series built on them doesn't. So are we okay with the squeeze theorem up here? Especially the bottom one. So if these sequences are like, you have least, middle, greatest, do we think that'll also be true if I start adding these things up? So instead of looking at the sequences, I'm going to add up a bunch of zeros. Hopefully it's easy to see what the left-hand side of this becomes. So you're just adding up a bunch of zeros, right? That'll always be 0. Or if I add up a bunch of these things, or if I add up a bunch of these things. I know this converges to 0, right? Actually, I don't even care that it converges to 0. I just know it converges. Does the one on the far right converge? How do we know?
The theorem you just talked about.
Yeah, so I'll call it P series. If the two series that are kind of bookending these inequalities converge, then what can we say about the middle one? Must better converge as well. So what did we just find? We find that this series, the absolute value of cosine of n over n squared converges. Are we done now? We found convergence. Can we say if it's absolute or if it's conditional? It's absolute, right? Why is it absolute? Why is it absolute and I don't have to go look at conditional convergence?
The theorem said if the absolute value of the series converges, then the series converges absolutely.
Right. So we didn't look at the series I gave you. We looked at the absolute value of that series. So yeah, absolute convergence supersedes conditional convergence. Think about it as unconditional convergence. There's I don't have to like give it the help of having some negative terms in the sum to help it converge. It converges with all the terms that are positive, or at least not negative. Questions? We good?
How about this one here? Oh, never mind, sorry.
What would you like to do?
Find the absolute value. So if I take the absolute value of -1 to the n times n to the 3, or n to the 3 over 3 to the n, does that alter this thing in any way? I believe n to the third will always be positive. I believe 3 to the n will always be positive. The alternation will stop happening, right? So this right here becomes n cubed over 3 to the n. Do I know anything about this series or this sequence? What are your suspicions? Oh, go ahead.
It's
It's increasing? So let's look at a few terms. 1/3 is 1/3. When n equals 2, I get 8/9. That's a bad sign. And then 20 is 27/27, so 1. 64/81. Uh-oh. It's not monotone, right? Okay, so this doesn't mean the alternating series test won't work, but what you might have to do is basically remove some terms, because eventually it starts decreasing, maybe, right? If there's some value of n where the series decreases, or where the sequence decreases after that point, then basically we can just pull off the first like few terms and make that, just treat those separately. But I don't know if the alternating series test is going to help me anyway, because I'm not convinced this thing goes to 0. At least not yet. We could write down a bunch more terms, but I would like to have something more efficient. So we're going to bring in a new thing called the ratio test. So basically the whole point of the ratio test is this. I want to let n get really big. I want to see what happens when n gets really big, specifically by dividing, like basically taking any two adjacent terms and dividing them by each other. And I want to see if a ratio, like as n gets really big, if a common ratio starts to like get approximated. So basically I'm trying to see if as n gets really big, does my technically non-geometric series start to mimic a geometric series? Because as n gets really big, like I'll start getting near some ratio. So that's the motivation. Why would we even try to make a non-geometric series behave like a geometric series? What does that help us with? Can we figure out if geometric series converge? Is it difficult? No. So if we have a geometric series, we have like really a lot simpler ways to figure out what they do, right? When does a geometric series converge? What's there's only one condition. What's that condition?
Ratio was someone between -1 and 1.
Between -1 and 1, right? So that kind of gives us these conditions. If that limit is less than 1, we have absolute convergence. If we have greater than 1, the series diverges. So hopefully those kind of are consistent with what you think about a geometric series. If the ratio is less than 1, it converges. If the ratio is bigger than 1, it diverges. So in treating these non-geometric series, trying to see if they behave like geometric series eventually, that's what we're doing here. In the case that the ratio is 1, then you haven't learned anything, unfortunately. We gotta try something else. So that's kind of a drawback to all the tests we're talking about is, like if you had a toolbox with only hammers in it, it's useful if you're dealing with nails, but sometimes you need something different. So after we kind of talk about all these things you could use, we'll talk about when it's appropriate to use a given one. So give you a couple more minutes to write, but are we okay with like the logic behind the way this is defined? So let's try to use it on that last series we just talked about that we kind of gave up on. I'm going to look at the ratios here. So I would like to look at this limit. What's the thing that makes a geometric series geometric? The ratio between what? Oh, not the thing that makes it converge, but like what is a geometric sequence? Has a common ratio, right? The common ratio basically means if I multiply a term by the common ratio, I'll get the next one, right? So because of that, that is why we look at the ratio between some term and the term right before it. Did I give you n-1 and n, or which one be consistent? No, okay. So maybe let's look at the denominator first. What's this denominator look like? The absolute value of what? -1 to the n times n cubed over 3 to the n, right? What's the numerator look like? -1 to the n plus 1 times n plus 1 cubed over 3 to the n plus 1. Looks pretty hectic, right? But are there things we can do to help out with that? What are the absolute values? Like, is there a way to simplify anything?
Usually we get the -1 to the n and the -1 to the n.
So the absolute values remove the alternation, right? And I think everything else is going to be strictly positive. So that makes this n plus 1. I really need to keep the limit operator. Actually, I'll just do this. Yeah. The limit as n goes to infinity of n plus 1 cubed over 3 to the n plus 1 over n cubed. I'll emphasize this a little more. Over 3 to the n. Does anything else simplify in a convenient way? Maybe it'd be helpful if we, instead of having this fraction within a fraction, I multiply by the reciprocal. So n plus 1 cubed over 3 times n to the, or 3 to the n plus 1 times 3 to the n over n cubed. Did that help?
Because the 3 n's cancel, right?
The 3 n's cancel.
Because you'd be able to separate 3 n's.
Right. Are we okay with this? That 3 to the n plus 1 equals 3 to the n times 3 to the 1. Okay, yeah, that's absolutely the way forward. So this limit, as n goes to infinity of n plus 1 cubed over 3n cubed, basically. Is that a limit we can look at? What does that limit become? Let's do this. I'm going to pull the 1/3 out. 1/3 times the limit as n goes to infinity of n plus 1 cubed over n cubed. What's the degree of the numerator? What's the degree of the denominator? Which means basically the numerator and denominator are growing, they're increasing at the same rate. Does that help you about what the limit might be? Should be 1. Another way we can think about this is, what is n plus 1 cubed? It is n cubed plus 3n squared plus 3n plus 3. Still all over n cubed. Maybe it's more clear that basically all the lower powers of n are going to get overwhelmed. So that's going to go to 1 as well. So basically my limit is 1/3. So a long way to go to get that limit. So we should be clear about what that tells us. Who cares? What does that value of 1/3 do for us?
It shows that it converges.
I have absolute convergence. So as n gets really big, this weird series we started with starts to behave, or not the series, but the absolute value of the series starts to behave like a geometric series with a common ratio of 1/3, which is within that range of common ratios that we know convergence.
Questions? All right,
I'll either see you Friday or I'll see you upstairs.